Okay, hello everybody. So this is just a quick introduction to the basic theory of electromagnetism for uh, this graduate level class. Now, unlike maybe an undergrad class, what we're going to start off with today are Maxwell's equations, which are, as you probably heard, the following four equations. You have the divergence of the electric field is given by 1 over this constant epsilon naught times the charge density rho. We also have the curl of the electric field is equal to minus the time derivative of the magnetic field. And in addition, we have that the divergence of the magnetic field is 0, and the curl of the magnetic field is mu naught, another constant, times current density J plus 1 over c squared, the change in the electric field as a function with time. Now, these are Maxwell's famous equations written in their differential form. And you've probably seen these on t-shirts and other contexts in quite a few places. However, they're not often what you use when you first learn about electricity and magnetism. These are the equations that specify what the electric fields and the magnetic fields look like. But they're not often what you use to calculate those fields. You use other rules. But what we will see over the course of this course is that these are the fundamental four equations of electricity and magnetism. But they are not the complete theory of electricity and magnetism. What these four equations tell us is how to calculate the electric field given charge distributions, current distributions, and they're obviously interrelated because there's both a magnetic field in the equation for the electric field and an electric field in the equation for the magnetic field. But these are not a complete theory. The reason being, it tells you what an electric field and a magnetic field are, but it doesn't tell you what they then do, what those things do to, say, the charge distribution or the current distribution. For that, we have one other equation, which is what's called the Lorentz force law, which is simply, which can be written various ways, but the way I like to write it, the force on a charge is just the charge times the electric field plus the cross product of the charge's velocity and the magnetic field. This is the equation that tells you how the charges and currents accelerate in response to these electric and magnetic fields. And then Maxwell's equations tell you how the electric and magnetic fields respond. And it turns out, except for one other equation, which we'll get to later, this is the complete theory. This tells you exactly how charges will move in response to each other in pretty much any situation, as long as things like quantum mechanics don't get involved. So the thing is, though, these aren't introduced as a complete theory. The way you usually learn about these equations is you build up to them through other equations. And what I want to do is just kind of recapitulate that way we usually learn about these equations so that you can remind yourself of where they come from. But what I'll do later is show you that these are actually more fundamental and more general than those earlier equations. So, how do we usually learn these equations? Well, we don't learn any of them to start with. The first thing we ever learn about, usually, again, this is assuming my experience, is what you consider is, what if I have a couple of charges, say Q1 and Q2? What's the force on these two charges due to their charge? Or what's the force on Q1 due to Q2 existing? Now, that's given by Coulomb's law, which is expressed in terms of where you can write basically the force on charge 1 due to charge 2 using the standard formula. One way you could write it is it's just Q1, Q2 over 4 pi epsilon naught times 1 over the distance between those two charges, which sometimes can be written as R12, and it goes like that squared. But if we want to be a little more general about this, we can take an origin of our coordinate system here, and we can define a vector R1 and a vector, this will be a little ugly, but we'll deal with it, R2 here. We can rewrite this as just instead Q1, Q2, 4 pi epsilon naught, 1 over the magnitude of R1 minus the magnitude of R2. Sorry, the magnitude of the difference between R1 minus R2 squared. Now the trick is, of course, as you know, this is not a force, this is the magnitude of the force. If you want to write this properly, you need to include the direction. And of course, if the charges are equal, that the force is directed along the line between these two. They either attract or repel, depending on their sign. And we can incorporate that by doing the following. The magnitude is the same over 4 pi epsilon naught. But now we need a vector. We need to give this a direction. And you could always write it as R12 hat, but it's actually a little more convenient to instead write that in terms of the following way. You just write it as the vector R1 minus R2 as a vector over the magnitude of R1 minus R2. That's just what that is, but now you don't have to worry about what the heck without having to write R12 as a separate thing. So this just becomes Q1 over Q2, 4 pi epsilon naught, 1 over R1 minus R2 cubed times R1 minus R2. So this is usually the first thing you learn, and you do various homework problems calculating this under various circumstances. Now, you can generalize, and the next thing you learn after you learn this particular rule is you learn how to generalize it. What if instead of having just two charges, we have one charge, which we'll call, say, Q, we could still call it 1, but yeah, let's call it 1. But we have a whole bunch of other charges, Q2, Q3, which is over here, Q4, which is hiding over here, etc. Well, since the previous expression was purely linear, there's the total charge on F1, the total force on charge 1 is just the sum for all I greater than 1 of F1I that we showed before. So all this is going to be is sum of Q1, Qi, dots are hard to draw with this little silly system, 4 pi epsilon naught over R1 minus Ri, where these are the positions of each of these individual charges, just the vector sum. And this is for all I greater than 1. Now, you can even go to other cases. So this is the total force. You can notice it's just proportional to Q1, so you can always write this, if you so desire, as Q1 times the sum over I greater than 1, just Qi 4 pi epsilon naught R1 minus Ri over R1 minus Ri cubed. Whoops. And I made a slight mistake, so we'll fix that. Those shouldn't be parentheses. They should be absolute value markers. So, and then somewhere along the line when people are telling you about this, you say, we call this thing the electric field generated by all of those other charges at the position R1. Notice it depends on where the charge is, but not the properties of the charge itself. You factor those out. And many students, when they first see this, go like, why did you do that? Why did you make me have to why do I have to calculate this thing instead of just calculate the force? Again, that's not obvious at this point in the calculation. Turns out that it's more convenient to calculate things. We'll see why over the course of this course. So this is if you have a bunch of discrete charges, but you can also write it for the case where you have, say, just a normal charge Q, and you have some distribution of charge, like maybe there's some positives over here, some negatives over here, and some continuous charge in between. We have a charge density that's what we'll call rho. In this case, we again define an origin of the coordinate system here. We call this vector R, this vector R prime, and basically we get the same expression, except now instead of having a discrete sum, we have an integral. So we have the force on charge Q is going to be the charge Q times, instead of a sum, an integral over the charge density over 4 pi epsilon naught. But now we have, instead of R1 minus Ri, we have R minus R prime over R minus R prime cubed. And we have to integrate this expression over all possible values of R prime. Notice this rho is a function of R prime, not R. So notice this. Rho has units of coulombs per meter cubed. This has meter cubed, so this has the same units as this. So again, we can identify this thing as the electric field at point R. And again, this decomposition, you go like, okay, I kind of see why it might be useful, but it's like, this seems like a definition for E. And what we'll see is it's not that. So after you learn this sort of stuff, which is all Coulomb's law, the next thing you usually learn is the first of actual Maxwell's equations, which is del dot E is rho over epsilon naught. But you don't learn it as something fundamental. You learn it as a trick to calculate electric fields. And you don't usually learn it in this differential form. You instead learn it in its integral form, which you can get from just taking this thing and integrating over a volume. So what we do is we imagine have some volume in space, which we'll call V. And we could say that the integral of this quantity, the divergence of E, integrated over that volume, So we integrate over all coordinates in that volume equals the integral of rho over E, epsilon naught, sorry, integrated over the same volume. Now, this side is actually pretty easy to evaluate. The epsilon naught can be pulled out because it's a constant. And then you have the integral of rho over the volume. That's the thing that's often called, that's the total charge enclosed by that volume. So the total charge inside this volume is that integral. This thing, though, what you have to do is use one of those various rules in vector calculus that relates the integral of a divergence to an integral, that relates the integral of a divergence over a volume to the integral of the vector itself dotted into the surface normal over the surface of this thing. So if this is the volume, this boundary is the surface. There is a direction associated everywhere on the surface because it points there, there. This says the component of E along that surface normal at every point, if you evaluate that, and you integrate that over the entire surface, you get something that equals charge enclosed. And you usually use this expression to figure out the electric field of systems with high degrees of symmetry. You know, like if you have a spherical charge, a sphere with uniform charge distribution on it, you can define a surface that looks, say, like that. You define a surface that is centered on that charge. I can't draw that terribly well, and you figure out what the electric field looks like. You know that, and it's, you know, you could basically show that the electric field of a spherically symmetric charge, you know, is radially outward and uniform, et cetera, et cetera. This is the sorts of cases you use it for, but it looks like just a trick to calculate the electric field in cases where this previous expression is awkward to calculate. And it turns out that's misleading. This expression is actually the fundamental one. Okay, so that's usually the first thing you learn in E&M as an undergrad. The next thing you learn in E&M is usually something about magnetic fields. Now, what's interesting is you don't learn magnetic fields the same way you learn about electric fields. If I asked you to calculate the force if I was asked you to calculate forces on things with magnetic fields, you don't initially think about calculating the force between two currents. That's not usually how it's taught. I mean, it turns out there is a rule that says if you have, say, a perfectly straight wire of a current flowing here, I1, and another current flowing down a wire here, I2, their wires going straight into the page, there is an expression for a magnetic force between those two, which is mu naught I1 I2 over 2 pi and the distance between those two wires. Now, the thing is, this is actually technically the force per unit length. So there is an expression like this, but it isn't the one you learn first. And part of the reason is this is an extremely special case. If you think about infinite straight wires, this is obviously a fairly generic case. The problem is there's no point charge for wires. Because a current fundamentally is charges in motion. So you can't define a point current. But it turns out there is an expression analogous to the Coulomb's law that you can write down. It's called the Biot-Savart law. And if you want it written down, it's Biot Savart law. This is the analogy of Coulomb's law. And the way to, and I'll just write down the final version. Let's consider a current distribution. So we have some places where charges are flowing this way, some places where charges are flowing that way. Throughout this region, there's a vector field J, because of course you need to know magnitude and direction to define a current. We want to know what kind of force that produces on a little bit of current further out. Now you could imagine there being a loop of wire and you're asked what's the force on this little bit of the wire. But we could be even more fundamental and just say there's a charge Q moving at a velocity V somewhere out there. That's the simplest unit of current we can talk about. Now, again, and I'll try and do this in slightly different colors to make it a little clearer. So again, we have an origin, our coordinate system. We can say this charge is currently at a position R. And we can also say these currents we're interested that generate a magnetic field are at some location R prime. And what we can do is write a generic expression for the force on Q when it's also moving at speed V. And it works out that that is Q times V cross, so it's a cross product, the integral of mu naught over 4 pi, just a constant, the current density at R prime crossed into R minus R prime over R minus R prime cubed, integrated over all possible values of dr prime. Now, and this thing is what we call the magnetic field at location R. Notice it depends on R, doesn't depend on R prime, that's integrated out, and it depends on the current density. So the force on a moving charge has this term. So this is where the Lorentz force law comes from. Generically, if you have electric and magnetic fields, you have Q times the E we had before, plus this part, which is from the magnetic field. This is where the Lorentz force law comes from. But you can also see why people don't tend to learn this early on, because it's obnoxious and involves vector cross products. It's not something you could easily write down in most situations. So this does exist, and some people do learn it this way. But most people don't learn how to calculate magnetic fields using this relatively complicated formula. They learn it from Ampere's law, which is, again, one of the fundamental ones, although it's not quite complete yet. Which is often written like this. The curl of B is mu naught J. Now, again, this isn't the form most people find useful. And that's in part because we usually use the integral form. So again, how do we integrate this? Well, in this case, we're not going to consider a volume. We're going to consider some sort of surface. So we have a surface here, just drawing shades to do that. It has some surface there that has a boundary, which can be defined by a vector that runs around it, which we'll call dl. Okay. Now, if we integrate both sides of this equation over that surface, we get del cross B, and we have to take the component of that through a surface, because the surface has surface normals on. So we have to dot that into the surface normal, and we have to be careful about our parentheses here. So, and then we integrate that over the 2 dimensions of this thing. So we're integrating this over the surface. This equals the integral of mu naught j over dot into the surface normal integrated over that surface, which sometimes you write as ds, but can also write if you're feeling appropriately pedantic, you can write it as d2r. Now, if we have current, and I'll do that in red. So if we have current of various types coming through this thing, what this half of the equation becomes is just basically the current flux through this surface. So it's mu naught times the enclosed current that goes through that surface. Okay, that's that side. What about this side? Well, here you use Stokes's law. The integral of a curl over a surface is equal to the integral of the magnetic field, just the raw vector field, along the length. And here you're just going along the boundary of this thing. And this is the usual expression you use. I mean, the standard one is if you have a wire here that carries a current I, you consider a surface, which I'll do in orange, you consider a loop that goes around that. The thing enclosed is mu naught I. So you can just say mu naught I, and your magnetic field goes around in the same direction, assuming it's uniform. You get the standard 2 pi, the distance, say this distance is rho, 2 pi rho times magnetic field. You get the standard expression for what magnetic field around straight wires looks like without having to do obnoxious cross products. So this is how you usually learn how to calculate magnetic fields. And again, it's treated more like a trick than something fundamental. The hints that something is going on here that these equations are more than just tricks usually comes at the next step when you're introduced to something called Faraday's law, which is the first one that explicitly relates electric and magnetic fields. It's this del cross E equals minus dB dt. Now, this is, again, the derivative form, but this is the one that says E and B are actually related to each other. Now, the way that we usually use this is, again, the integral form. We, again, take an integral over some surface. The integral of del cross E integrated dot, and we can basically take the surface normal times the surface and just do that, equals minus ddt integral of b dot ds. Now notice what I did here. I just pulled the ddt out of the integral. That's because there's nothing here that involves time. This thing is minus this quantity we call the magnetic flux, phi. So if we have magnetic field lines, so show B in this color, coming through the loop, then changes in the magnetic field is a change in the magnetic flux. On this side, we do the same rule as before. Stokes's law turns this into integral E dot dl. So this means that if you have a changing magnetic flux, you will have an electric field, E, going around this loop. This is, of course, the basis of like most electric power. You have changing magnetic field lines that drive currents around loops, which you could then tap off of and generate things. Now, one thing I'm going to ask you here is you get used to using this expression because calculating the magnetic flux is easier than doing obnoxious cross products. But this thing is actually a little cleaner defined than this, because one thing that's sometimes a little tricky to understand is what happens if the loop moves? If this is like a wire loop that's falling, you can go, oh yeah, that's just a magnetic flux, I'll treat it that way. But for example, what if this is perfectly well defined and handles both cases perfectly fine, but physical interpretations can be different. If you have a wire moving through a magnetic field, you go, oh, okay, there's a little charge here. There's a little charge here. It's moving down. It's in a magnetic field. It feels like it's getting pushed. Fine. But what if the magnetic field is getting stronger? That also produces the same effect. But why? And this is something we'll come back to. It turns out that this is a more generic expression for how these two things interact. Anyway, at this point, we have a first order expression for the various things. We've basically gotten most of the rules. The one we haven't gotten yet is, which you often hear somewhere along the road, is del dot B is 0. All that reflects is the fact that magnetic field lines always form nice closed loops. That's just the nature of magnetic fields. You're usually introduced to it at some point, but maybe aren't like, you don't learn it in quite as much detail, except when you're drawing. So at this point, we have this equation, which is kind of like, sounds like a trick to evaluate, whoops, and that should be a dot, not a cross, a way to evaluate Coulomb's law. You learn this, which is something. You learn this, and you learn Ampere's law as a way to evaluate magnetic fields. And you get the force law. Now, the one thing, and then at this point, you're usually taught this isn't complete. We've forgotten a term. There needs to be another term here. And this is where Maxwell gets involved and is one of the first kind of things I want to highlight a bit. This particular expression has a problem. It is intrinsically inconsistent. And I want to show you why. What is the problem with this expression? Well, what is wrong with this expression? Intrinsically, nothing much looks wrong with it. I mean, it's what you use to calculate other things. But to see what's wrong with it, take the divergence of both sides of this equation. So let's take the divergence of this side, and let's take the divergence of this side. Well, mu naught's a constant, so we don't have to take the divergence of that, but we can take the divergence of this. Okay, this side, this is the divergence of a curl. Mathematically, that has to be 0. You can prove this. I'm going to be a physicist and say that it's provable. This says 0 is del that J can never have a divergence. Now, in most cases where you've used Ampere's law, that's perfectly reasonable. But it's not a fundamental truth of the universe. Remember what, if del dot J is 0, that has implications. Again, we usually don't think about this in this form, so we can instead, again, integrate it over a volume. Say we have some volume of space. Del dot J of d3r is just the integral, using, again, Gauss's law, is the integral of J itself dot ds integrated over the surface of a volume. So this says every volume in space, so if I draw a volume in space here, this says that that the integral of the current density through that surface has to be 0. And the thing is, I can create conditions where that's not true. The easiest way, take a block of photoelectric metal and shine UV light on it. The UV light goes in and starts knocking electrons off of this thing in all directions. So there are electrons leaving this object. I can define a volume where those electrons are flying out of. There is a net current into this volume because electrons are negatively charged. There is a net flux of current through this surface. This equation doesn't hold here. This equation this version of Ampere's law doesn't work here. This is what Maxwell realized. He realized that there needed to be something else here. And he proposed to add one specific term. And at first, it doesn't look obvious why it should work. But what he said is the real expression is del cross B equals mu naught J plus mu naught epsilon naught dE dt. Why does this work? Well, let's do the same trick we did before. Let's take the divergence of both sides. This is still del dot del cross B, which is going to be 0, equals this thing, which is mu naught del dot J, and I'll just pull the mu naught out because it's easier, plus epsilon naught del dot ddt of E. Okay, so there's now an extra term there. Important thing, time derivatives and spatial derivatives commute, so we can rewrite this. Mu naught del dot J plus epsilon naught ddt del dot E. Wait a minute, we know what that is. That's given by Gauss's law. Remember, del dot E is rho over epsilon naught. So this is now del dot J plus, this becomes rho over epsilon naught's a constant, cancels out that one, plus d rho dt. Got it? We are saying that is 0. And that is true. Again, do the integral. If we integrate this over a volume, this combination of two terms, what do we get? Well, integral of del dot J is, again, the integral over the surface of J dot ds. So that's the net current flow in or out, plus the time derivative of the integral of rho over the entire volume, but that's the charge enclosed in that volume. we're saying that is 0. That makes sense. Let's go back to our previous situation where we had a blob, and inside that volume of space, we have some material that is releasing electrons. Sorry, that one arrow isn't going in the right direction, so I should raise that a little bit here. Draw that properly. So we have a bunch of electrons going through this surface. So what is the net current flow? Well, there's a net, in this case, the integral of j dot ds is less than 0 because the surface normal always points outward, and the current, because electrons are negative, is flowing inward. But dq enclosed dt, as time's going on, these electrons are leaving this region, making this thing more and more positively charged. So this is greater than 0. This is okay. What this expression actually represents is charge conservation. This says that you can never create or destroy a net charge, you can just move it. If the charge density at a given location is changing, it's only changing because charges are moving into or out of that region. And that's how charges seem to work in our system, in our universe. We have never seen a net charge either appear or disappear. So that brings us all the way back to this set. If we add that correction back, and that can be rewritten as a constant here, and as long as we specify that charge is conserved, which means del dot j plus d rho dt is always 0 at all times in all places, this is actually a self-consistent, unique theory. And again, this is not something that's yet obvious. It's a bunch of equations that tell us something about electric fields, how objects respond to electric fields, and that charge is conserved. But what I want to show you now is that these are fundamental equations. That these 4 equations for the electric and magnetic field are the only information you need. These uniquely specify the electric and magnetic field and always specify the structure of the electric and magnetic fields. Thus, this is a complete theory. There's no ambiguity here. Whereas for things like, say, Coulomb's law, there is ambiguity. What we need to recognize, and what we'll talk a little bit more about, is that these are the generic fundamental expressions. Things like Coulomb's law and the Biot-Savart law are valid in specific cases. They're the easiest ones to use sometimes, and we will use them, but they are not the fundamental ones. And we will be approaching how to understand what's fundamental about this and what that tells us about the structure of electric and magnetic fields throughout the course of this course. But I think that's enough for this one video. If you have any questions, please let me know, and let me know what you think about this overall structure. Thank you very much for your time and attention.